I'm not going to be going through too much theory. Pretty much just going to be going through prep for this test. All right, so the concepts that are going to come up are nomenclature, IUPAC, chirality, Newman projections, chairs, maybe a little bit of degree of unsaturation, and substitution reaction. All right, so again, I'm not going to be going through too much theory. I'm going to be going through problem solving. All right, so I'm going to pull up this practice that we're going to go through. See if I can share my screen. Very cool. And hopefully, I really hope this you're able to still see me on the board because I'm going to be doing a lot of drawing on the board. If not, I'll reiterate some stuff, hopefully with some of these tools. All right. Anyways, this first question. So the first question is getting at Newman's. All right. So the lowest energy eclipse conformation. All right. So remember our conformations of a Newman are anti. Then we have gauche. Then we have a partial eclipse. And then a full eclipse. All right, and that's in order of stability. All right, so what this is asking is basically which of the two eclipsed formations is of a better stability. All right, so the greater the stability, the less energy, and less it's less likely to snap into another conformation. All right, so what we're looking for is basically the partial eclipsed form. All right, so if I were to draw a couple of these out, okay, so let me draw B out. So B is as such in the bond line, and to a Newman looks like this. So the methyl is going to be pointing up on the front carbon, and the two hydrogens, implied hydrogens, are going to be coming off left and right. All right, so again, let me try to draw this on here. Up, hydrogen, hydrogen, front carbon. That carbon, methyl is also going up. Hydrogen, hydrogen. Okay. As we can see, this is a fully eclipsed. All right. That's no bueno. That's very unstable. That's the highest energy. All right. So what we're looking for is a partial eclipsed. All right. So an eclipse formation, but partial, not full. Okay. So let me draw A, for example. All right. So on the front carbon, we see that methyl being wedged. All right, so off the front carbon, that's going to be coming out of the plane, out of the paper at us. And so when we turn to look at the other perspective, it's going to be coming off to the right. Okay, and we have our two hydrogens. Drawing our back carbon, all right, we have the methyl coming downwards. And then, of course, our two implied hydrogens. Okay, so this is an eclipse formation. All right, let me go ahead and draw this. So the front carbon's got a methyl going off to the right, and then you have your two other hydrogens. That's the front carbon. Back carbon, you have the methyl pointing down. You have your two hydrogens. All right, so this is eclipsed, and it is partial, which is exactly what we're looking for. All right, so A would be our answer. All right. Moving on. So the next question is asking about just basically which of the following Newmans is that conformation for butane. All right, as we can see, we need two methyls pointing up, and it needs to be butane at all, really. So I can almost guarantee you're going to get a question that asks you something like this, and something that you need to make sure of is if it is if it is even the molecule that we're looking for. All right, so all of these are butane, but not all of them are the correct conformation that we're looking for. All right, so if we're looking at the front carbon, you have and you're looking at it from the Newman perspective, you have the methyl pointing up. And on the back carbon, it's doing the same. And just off of first glance, there's only one of these that really match that, which would be A. All right, so A would be our answer for this question. Right, so moving along, which Newman structure represents 2,3-dimethyl-butane? All right, so let's just draw that real quick. You got butane 2,3, so you got a methyl coming off first and third. All right, so a couple of these aren't even that molecule. All right, so as we can see, so let me just go along, just annotate on this. All right, so all right, so this is our dimethylbutane. As we can see from our front carbon, you have two methyls coming off of that, right? And off the back carbon, you have two methyls coming off of that. All right, if we look at our back carbon on B and D, it doesn't match that at all. So on the front carbon on D, you have three methyls coming off of the front carbon. That's not 2,3-dimethylbutane. And if you look at the back carbon on B, that's not the same either. All right, so again, you got to make sure, and unfortunately that this practice question does have the hint there. You got to make sure that the Newman projection is even for the correct molecule. All right, and so A and C are now a contender. They are, in fact, 2,3-dimethylbutane, but they're a different conformation. All right, it says which one represents the most stable. All right, and as we can see, if we're looking at A, all of those methyl groups are sort of crowding each other out. All right, contrary to C, in which you have a couple over here and a couple on the opposite end of the spectrum. All right, so C is going to be your more stable Newman projection between A and C. Okay. Moving along. Draw the bond line, choose the bond line that represents a gauche conformation. All right, so again, this gets into having to be able to go from bond line to a Newman. All right, and we've drawn it, and so you should be able to, at least with butane, be able to recognize the patterns involved in going from this. All right, as we can see, A is going to be a fully eclipsed. All right, C is going to be anti. All right, those aren't gauche. All right, so let's check B and D. All right, so let's draw B. So our front carbon has a methyl going into the plane of the board. All right, so if we were going to shift our perspective to look at the Newman, we're going to see that be going left. CH3. All right. Then you fill in the rest with the applied hydrogens that would be there. And you have your back carbon. All right. You have the methyl going down, which would imply that the two other hydrogens are going left and right. Okay. Is this gauche? No, not at all. This is an eclipse conformation. All right. So just by process of elimination, we can see that our answer is going to be D, but let me draw that out. Okay. So our front carbon has a downwards left methyl. Okay. Left because it's dashed, which would imply that the other two groups are going to be your hydrogens. Now, back carbon, you have a methyl coming downwards. And then you have your two implied hydrogens. So just in case that this is hard to visualize, let me draw this out. All right, so off the front carbon, you have your methyl going left, which would imply that you have your other two groups, your implied hydrogens. Now off the back carbon, you can see the back carbon, which is that one. All right, you have a methyl, and then your implied hydrogens. All right, now this is gauche. Why is it gauche? Because it's in a staggered conformation, and the two biggest groups, so the big group taking space off the front carbon, is next to, relatively, is next to, one rotation next to the biggest group coming off the back carbon. All right, so the methyl off the front is next to the methyl off the back and staggered, making this our gauche conformation. Cool. All right. Let's keep on going. All right. 5. Okay. So determine whether or not this is chiral, meso compound, or achiral. All right. So basically, this is all this is asking is, does this molecule have a chiral center? All right. I'm sure there's going to be a meso example later, but let's just draw this. All right. So the bracket in that bicycloheptane name tells us that we have a bridge with one carbon on it. All right. And on one side of that bridge, you have one carbon. And on the other side of the bridge, you have 3 carbons. All right. Now, if we were to look at this molecule, And again, let me draw this on the screen. If we were to look at this molecule, is there any given carbon that has 4 different groups coming off of it? So just take a second and assess that. All right. The answer would be no. There's not a carbon on this molecule that has 4 different groups coming off of it. Each one of them either has 2 hydrogens, all right, a lot of them are CH2s. And if you were to look at your bridge heads, those are both CHs. And if you were to trek along your path around the ring, you're not going to get any point of difference. All right. So overall, this is going to be achiral because there is no chiral centers. Okay. So A is going to be our answer. All right. Now, if you look at 6, all right, which of the following is the cis isomer? So remember, so these Newman projections look fairly complicated, which is okay, because all that we're looking for is the direction in which the things that are pointing. All right, remember, cis is same, trans is opposite. All right, so cis pointing in the same direction. So you want your biggest groups pointing in the same direction. As we can see, B is it has one methyl going up and another methyl going downwards. All right. And given that that's not the case, that would make B not a valid option, which would also make D not an answer choice. Let's look at C. C, you have the methyl going downwards and you have the methyl going upwards, which is, again, that would be considered trans. So the only true answer here that would be considered cis would be A. Okay. It's going to be A. Moving along. Get rid of some of this stuff. All right, so here it's looking for the correct IUPAC name. Okay. So all of this is really, second, there's a technical difficulty. All right. So IUPAC, again, we need to know the parent chain. All right. So I'll draw this up on the board as well. If it's visible, hopefully. Okay. We want the longest chain and the chain that contains all of our substituents. All right. And the one that does that would be as follows. All right. So starting from the bottom, this would be carbon 1, 2, 3, 4, 5, 6, 7. All right. So I'll number that on the screen as well. 1, 2, 2. 2, 3, 4, 5, 6, 7. All right. So right off the bat, we can eliminate C and D because we don't have a pentane. All right. We have a heptane. All right. And we started from the bottom instead of the top because if we started from the top, we wouldn't get the lowest numbered possible. Starting from the bottom gives us 2, 3, 6. And starting from the top gives us 2, 5, 6. And that's not any better. All right. So we want the lowest number. So we want the parent chain with all of our substituents, and we start in the direction that would give us the lowest number possible. All right. So our answer here is going to be B. Okay. Moving on. What is the index of hydrogen deficiency for this molecule? All right. So I'll draw up here. So the index of hydrogen deficiency, again, I said I'm not going to get too much into theory. It's just a way that we measure how saturated something is. So you can call this index of hydrogen deficiency or degree of unsaturation. All right. So if you have a double bond, that would remove a couple hydrogens, right? If you have a ring, that would do the same. All right. So the more bonds that you're having within the molecule and the more rings that you have within the molecule, the less saturated that molecule is going to be. It's going to be hydrogen deficient. Okay. So the general, if you want to make this, if you want to write this down, I'll write it here on the screen as well. So our formula is going to be 2 C as in carbon plus 2 plus nitrogen minus halogen minus hydrogen over 2. Okay. So the way that I like to memorize this is everything is added except halogens and hydrogens are subtracted. All right. So we got 2C plus 2 plus nitrogen minus the halogens and hydrogens. All right. In this molecule, we don't have any halogens. All right. So let's fill in the formula. All right. So we got 2, we have 5 carbons plus 2 plus 1 nitrogen minus 11 hydrogens. All right. The oxygens are not at play here in the formula. All right. This is going to simplify to 13 minus 11 over 2, which is going to give us 2 over 2, and our answer is going to be 1. All right. That's it. That's all it's asking. All right. So this is one of the maybe 2 formulas that you'll need to know for organic chemistry 1, at least here at FAU. Okay. So let me erase some of this and keep on trucking. Which of the following stereoisomers is not chiral? All right. Not chiral. So hopefully you guys can see this on the board a little bit. In fact, I'll zoom in ever so slightly. Hopefully that helps. All right. So which of the following is not chiral? All right. So what I like to do is I tend to like to make them a bit more explicit, in which I'd like to draw these out. Okay. So if I were to draw A out in 2D, I would get the following. All right. And remember, again, I'm not going too much into theory, but up was wedged, down was dashed. All right. So we got 1 carbon that has the methyl, which was being wedged. We got the other on the other side being dashed. All right. So this would be A. B would be as follows. All right. We got 1 going downwards. So that would imply that was dashed. All right, and 2 carbons over, we have a methyl that was going upwards, so that implies that that was wedged. All right, so that would be B. So this is A, B, and then we need C. All right. So C, you have one pointing downward, which implies that that was dashed. And you have the carbon next to it has a methyl, which is going upward, which was implied that it was wedged. All right. Now, which of the following is not chiral? So again, no chiral center or a meso compound. Okay. Let me stop screen share just so this is explicit. Okay. So which of the following is not chiral? All right. If we were to look at C, and we were to look at this carbon, all right, do we have 4 different groups? We have a methyl, so that carbon has 3 H's. You have a CH2, and you have a CH, and you have an implied hydrogen. 4 different groups. All right, so that's chiral center. And same goes for that carbon. All right, so this molecule does in fact have chiral centers, making this a chiral molecule. All right, what about this one? We have this carbon, we have a methyl coming off of it, and you have an implied hydrogen. All right, so there's 2 different groups. You have a CH2, CH2. Okay, so we continue to go around the ring to see if there's a point of difference. All right, then you're met with a CH, and you're met with another CH2. Cool, there's a point of difference between our 2 other different groups. So that molecule does have, or that carbon does have 4 different groups, in which the same is going to be at play for that carbon as well. Okay, so both of these carbons are in fact chiral. What about this one? All right, we have this carbon that has a methyl, implied hydrogen. That's 2 groups. Okay, that's cool. All right, then you go around the ring, CH2, CH2. All right, we got to continue around the ring. CH2, CH2. Got to keep going. CH, and you have your methyl. Is there a point of difference between each side of the ring that would give us 4 different groups in total? No. And the same would be true for coming from this end and looking at that carbon as well. All right, so this does not have chiral centers because those that are being considered as a chiral center don't have 4 different groups coming off of them. All right, so some of these you would have to assess a bit more thorough like that. All right, and let me just throw out there, if B, hypothetically, again, if this was like this, all right, say you have a chiral molecule here, and let's just say hypothetically, this would be R. All right, and let's just say hypothetically that this chiral molecule, this chiral carbon would be S. All right, and you have an internal plane of symmetry. All right, those opposite configurations are going to cancel each other out. This is basically a racemic mixture on itself. All right, making this a meso compound and overall achiral. All right. When you don't need to worry about meso compounds if there is no internal plane of symmetry. The only time you need to worry about if something is a meso compound is if there is in fact an internal plane of symmetry. And if you have opposing configurations, then the overall chirality of it is the fact that it's not chiral at all. Okay, just wanted to throw that out there. So going back, let me share my screen. The answer to our question would be A. Okay. Did not have chiral centers. from 10. This is going into, again, that formula. All right, I'm not going to waste time on that one. All you would do is count up your hydrogens, count up your carbons, and that oxygen is not included anyways in the formula. All right, and so you would just plug in to the formula as we did. Okay. About 11. Which of these is a constitutional isomer of that molecule? Okay, so I tend to like to double check my formulas, period, because if it's a different formula, then it's a different molecule altogether. Okay, so if we look at A, let's just count up hydrogens, because that's sometimes a good way to look at this. All right, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have H11. That's not even our formula at all. All right. What about B? All right, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. H9. Okay, that's a contender. C. All right. We got 1, 2, 3, 6. This is no longer a competitor. All right, what about D? D, we have 1, 2, 3, 5, 6. Great. I could be missing here, but as far as I can tell, our only real option here that aligns as such, remember, because the definition of constitutional isomer is the same formula, different connectivity, in which B is the only true competitor here. Okay. So B's going to be right. What about, well, all right, so there's a little formula that we need to know. Okay. The enantiomeric excess. So we have, what we do is we do the R minus S plus, or over R plus S. And this is in absolute value, right? So in order to solve this problem, you have to be given the quantity of your RNS, right? So which we're given, all right? So we got 3, not plus. Like that. We got 3 minus 7 over 3 plus 7, giving us 4 over 10, giving us 40%. Our answer is D. That's it. All right. Let's keep on with it. How many chiral centers are on this molecule? All right, I'm not going to waste time to draw this on the board. Hopefully we can do this together on the screen. All right. Let's look at, see if I can zoom in a little bit here. So this would be a chiral carbon. So with this one, we have 4 different groups. Let's continue around. That one is not, but these 2 are in fact chiral centers. They might not look it, but if you were to trek around the ring, all right, so here we have a hydrogen, all right, CH2, CH2, but here's a CH2, and then you're met with a carbon attached to a bunch of different stuff, okay? And then you, in front of it, you have a CH. 4 different groups. And same idea on this carbon as well. All right. So this molecule, if I were to draw this out, what you'll get is that which that is not a chiral center. All right. So the answer to this question is C. Okay. So this question, we need to consider really the importance of numbering of priority correct. Okay. So to properly prioritize, we do atomic number. All right. So the first point of difference, so we're assessing what's directly attached to our chiral carbon here. All right. The first thing that the first priority coming off of that is the oxygen. So that would be 1. Hydrogen here would be 4. All right. And as we can see, B and A and B are not even an answer choice because of what we just said. Okay, so again, here, write this 1. Right. Now, if you were to look at the triple bond versus the tert butyl, all right, that looks like they are of equal priority, but if you were to draw out the points of differences, in which I'm not going to do here, but I'll just tell you that this carbon triple bonded to this carbon, all right, is of higher priority than this carbon attached to 3 separate bonds. All right, so this is going to be priority 2, this will be priority 3, in which D is going to be the answer. Okay. Okay, R and S. Figured it would come up. So we need to first and foremost assign priority. All right. Let's assign priority again off of that carbon that's indicated. All right. So let's just say this is the carbon. Let's just say this is the carbon that's indicated. You have an alcohol, which would be first priority. And we have something that's wedged. Okay. So if we're comparing carbons now, if we're looking at this carbon, that outweighs, again, we have that's attached to an oxygen and attached to an oxygen, which is much better than either of these other carbons. All right, so it's going to be 2. All right, if you're going to go around the ring, you would see that coming off in this direction, you're going to get priority 3 here. All right. So what we do is, in order to mitigate the mental gymnastics involved, right, we ignore the dashed. We ignore what's in the back initially. All right, so let's ignore that and we count up. All right, so 2, 3, 4. This looks like S. All right, and was 1 or a 3 priority the thing that we ignored? Yes. So we flip. So really, Our configuration is R. And our answer is A. Right? So that's what I like to do. I ignore what's in the back. So I ignore what's dashed. I count up what's remaining in that direction. And if if the thing that I ignored was a 1 or a 3 priority, then I have to flip. Okay, that's the way that I do it. That's the way that I was taught. I'm not sure if he did that in lecture, but that's the way that I was taught, in which that takes care of having to try to picture it being done from a different view and doing the mental gymnastics involved. So So coming off of that carbon, we have a dashed hydrogen. That's going to be our 4th priority. Okay. We have this group here. This group over here. If you were to assess the various points of difference, what you'll find is that this group over here is going to be 1st priority. Over here, it's going to be 2nd priority. Methyl here. 3rd. So again, ignore what's in the back. Hydrogen's in the back. 1, 2, 3. Looks like S. Was what we ignored, is what was dashed a 1 or a 3? No. So we can keep it as S. That would be our answer. Okay. $17. So we're assessing this red carbon. Okay. In which this one, we have a methyl that is dashed, which would mean that we have applied hydrogen. It's wedged. The other group. Now, if we prioritize, you're going to obviously get an H as 4th priority. The carbons up here that are also have the oxygens involved is going to be our 1st priority. Then you have this carbon attached to other carbons that outweighs our methyl, which is simply attached to. All right, so we ignore what's in the back. Okay, ignore what's in the back. One, two, three. Then we have what configuration? We should be getting is you know what? Mistake. looking at our first points of difference. Really, we should be getting, so this carbon here is attached to two other carbons versus this carbon here, which is attached to a carbon and two hydrogens. What's better? Okay, so if we ignore what's in the back, we ignore dash, 2, 4. All right, this looks like R. But was what we ignored a 1 or a 3? Yes. Flip. And we get S. Okay. Pardon the mishap. Just had to double check it myself. It happens to all of us. All right. Leave that there just for a second. So you can make any corrections. Okay. So this gets into the relationship between enantiomers and diastereomers. If you were to do the RNS, all right, it's the way that I always like to do it. So this is going to be R. Okay. Kind of doing this along. So, yes. Okay, so see how you go from R, R, S, S. Each chiral carbon changed configurations. All right, so if all of them change configuration, you're going to get an enantiomer. All right, but if some, not all, then it's going to be a diastereomer. Okay, so our answer is going to be A. Right? Solvent best for SN2. Okay, so I just did a video on SN1, SN2. It's a very broad stroke review. There's not too much practice problems involved in that, but hopefully it was enough help in which I did go over this. You do need to know it. SN1 favors polar protic. SN2 favors polar aprotic. All right, the solvent does make a difference. Nonpolar is not favorable for either of these types of reactions. SN2 is best when it's with a polar aprotic solvent. Okay. Now this number 20, all right, this is what we call an alene. Maybe spelling this right. All right. I highly recommend you look up just a couple examples of this, but the answer to this question is going to be no. All right. This gets into something called axial chirality or axial symmetry, in which it doesn't look like this molecule can even remotely be chiral because of the pi bonds involved, but it can be. And this would be an example of which one of one that could be. Right? So again, I'm not redrawing this same molecule. I'm redrawing a molecule that could be considered chiral, for example. All right? So this would be considered chiral. Right? If you were to look at each end, if you were to look at this carbon, all right, you have two different substituents coming off of it. And if you were to look at the other end, you have two different substituents coming off of it, right? Right. That is something that helps the chirality, or that's something that helps this molecule have or exhibit some sense of axial symmetry or axial chirality. All right. You could piece this together on your, you could actually build this on your model set if you have one, but if you do not, this should be enough info. I doubt that you're going to get an answer that has like 4 different allenes. It's essentially going to ask you, or it might just give you a molecule, an allene, and ask you if it's chiral or achiral, or something along the lines like this problem is asking. Okay, so if you want to look that up, it's called allenes, and the concept is axial chirality. We're not going to get into today, but hopefully this example of a chiral allene should be just enough. Keep on trying. Okay, so we're getting into reactions. All right. The transition states are the intermediate steps. All right. So if I were to draw this out, you have reactants, products, making this a transition. You have reactants, products, making this a transition. You have reactants, products, making this a transition. So we have 3 transition states. Okay. So how many intermediates are involved? So we have, so our initial and we have our final, all right? These would be considered transition states, but that's different than it being an intermediate, okay? These values would be considered your intermediates between the products that we're actually trying to form. All right, it looks a little bit different. I might have worded that a little bit weird, but the above question, to just go back 15 seconds or so, these hills are transition states, but these valleys are inter. Okay, so our answer should be 2. Okay. Intramolecular reaction. All right, so I'm going to try to draw this on the board. Okay. Draw this on the board. Okay. So we have N, right, that's methyl. I think that's it, right? Yeah, I think so. Okay. It's asking basically for the correct product that would happen after undergoing an SN2 intramolecular reaction. All right. So again, I touched base on this in another video. All right. It's a broad stroke overview of SN1, SN2, in which I do at the very end touch on intramolecular reactions. All right. But what's going to happen is that this leaving group is going to leave, leaving a partial positive, all right? And that nitrogen with the lone pair is going to act as your nucleophile to go attack that carbocation. So that is what's going to be occurring, all right? A bond is going to be made between this nitrogen and that carbocation, right? So what you should end up with is something like, let me see, what is this? The nitrogen that has a methyl, it's making a bond with that. Holding it into a ring. And this one gets left alone. And that carbon is making 4 bonds. It's going to be positively charged. So just to illustrate one of these, say hypothetically that that was your carbocation. All right, and that nitrogen is now making a bond with that carbocation. So if I'm going to number this, I can go 1, 2, 1. All right. If hypothetically it says 2 moles or multiple moles or excess of your reaction is going to be occurring, then it might also happen again. All right. It's not going to occur in this example because that nitrogen doesn't have a lone pair again to react on itself. But if you did have extra nucleophilicity, I guess you could say, by way of that nitrogen having an extra lone pair that it can use to attack a carbocation again, then it will do so. All right. So if you do get a question that says that something's in excess, or you have 2 moles of your reagent, that means it's probably going to happen again. All right. That's not going to come up in this. I'm not trying to confuse anybody. But again, the intramolecular reaction, I did touch on it in the prior video. If it's unclear now, watch that, right, to the very end. But your leaching group is going to leave, and your nitrogen with the lone pair is going to act as the nucleophile to go attack itself, which will tend to form a ring as such. Okay. Let's go back to so this gets into a little bit of theory, right? The question is, in an SN2 reaction, what happens? All right. And I did, again, touch on this multiple times throughout previous video on SN1, SN2. All right, SN1 occurs in 2 steps. All right, the leaving group leaves, then the nucleophile comes in to attack the carbocation. SN2 occurs in 1 step. The leaving group leaves and the nucleophile attacks the carbocation at the same time. All right, and the only answer choice here that illustrates that is C. Okay. B would not be an answer choice at all, even if it were asking about SN1, because again, you have to have that leaving group leave in order for there to be a carbocation, period. All right. It's just in SN2, the leaving group leaves and their carbocation attacks at the same time. Okay. All right. What's the major product? All right. So we have Na. I'm going to use the board for this. All right. So what's the major product of the following substitution? All right. So we have NaOPH plus, what was it, 2 chlorobutane. All right. I tend to like to draw everything in. All right. So 2 chlorobutane plus pH is just short for a benzene ring. Okay. Okay. And an SN2 reaction, remember, or a substitution reaction in general, your salts are going to dissolve. All right, so if you have a polar solvent, unless it says otherwise, you can assume that your salt here is going to dissolve away or dissociate, leaving you with Na plus as a cation in your OPH as your anion, and that anion is always going to be what acts as your nucleophile. Okay, so we have the leaving group that leaving your positive carbocation there, in which the lone pairs on this nitrogen are going to be used to go and attack that carbocation. All right. So the result of that is a substitution. All right. That oxygen is using its lone pair to go make a bond with that carbocation. And that's it. All right. So let's see if one of our answer choices reflect what I just did. All right. Hopefully, because that would be pretty free. Cool. B. All right. B is going to be our answer choice. Let's continue trucking. Major product of the SN2 substitution in tert-butyl chloride and ethanol. All right. So again, we're gonna make a note of that while I draw this up here on the board. All right. This together. All right. We have tert-butyl chloride. Plus ethanol. All right. So it tells us here, again, let me go back to the board. It tells us here that you have an SN1 reaction occurring. But if it did not, you can know that an SN1 reaction is going to be occurring because that is going to be a tertiary substrate. Right? Again, I'm not going to go into all of that again. That was in a prior video. But that tertiary substrate is why the question is even prompting you to think about SN. All right. What's going to happen is that chlorine is going to leave, leaving you with a tertiary carbocation. Okay. And you have your OH here. That's going to come in and act as the nucleophile. Right? So that tert-butyl group is an oxygen now with the ethane. Okay. Let's see if any of our answer choices like that. Yes, it does. All right. B is going to be our answer. Okay. B is going to be our answer. What is the major product of the following reaction? All right. So it's not really a hint here what it's giving you in those typo, but you need to determine if an SN1 reaction is occurring. Okay. So we have, not only do we have a, so we have a primary, here up on the screen, primary, tertiary. All right. We have a polar protic going on here. Okay. So given that you have a tertiary carbocation that would be there and a polar protic solvent, all right, in my opinion, you would tend to have an SN1 reaction occur. All right, so your intermediate, in my opinion, yeah. All right, your OH is going to come along. Back. Bond. Everything else. So in my opinion, our answer choice is going to be A. If I'm completely wrong and somebody knows better, please don't hesitate to make that correction. If, again, hypothetically, say that it tells you 2 moles of hydroxide, then this second leaving group is probably going to leave. And that's going to come in and give you answer choice B. All right. And if we were assuming an SN2 reaction that would occur, then C would be your answer choice. But again, in my opinion, I believe that we're having an SN1 reaction. Okay. Carrying on. So I'm going to draw this one out. So this question gives you a chair. Good. All right, and we got, it has a methyl and it has, right, and we got and with negatively charged sulfur. All right, so the question is, what's the following product or products from this substitution? All right, so again, I walked through an example just like this on the previous video, but you have to be able to delineate whether or not you have an SN1 or an SN2 reaction occurring. All right, so is that a primary, secondary, tertiary substrate? It's secondary. All right, so now we look into, that's in a gray area. If we look into the nucleophile, we can see that it's a strong nucleophile. So secondary plus a strong nucleophile gives us an SN2 reaction. Okay. SN2 reactions do not create racemic mixtures. All right. SN1 reactions do. They have inversion and retention of the stereochemistry. But SN2 reactions do not. All right. They only have one major product, not a mixture. So C is not even C. I'll pull up the product, the problem again. But C, a mixture of A and B, is not the case. All right. So if I were to draw this out in 2D, right? Start to drill this out in 2D. We have a methyl. All right. But let's just ambiguously pick which one of these carbons has our chlorine. All right. Our chlorine is also on our chart pointing downwards. And in 2D, that implies dashed. All right. So if you have something in 2D that's dashed, you're going to be ending up drawing it downwards on your chair. All right. So that implies that we have a dashed chlorine. And if we're to draw the rest out, 2 over, that's also pointing downwards. Be a dash methyl. All right. Remember, stereochemistry flips, right? Flips stereochemistry. Stereochem. All right. So what was dashed, the product is going to be wedged. All right. So product here is going to be a wedged leave this here just to show that. All right. Now let's go back and see if, in fact, let me share the screen. Right. So B is going to be our answer. Okay, not A, because A would imply that it did not flip its stereochemistry, and that needs to happen in an SN2 reaction. Okay. All right, 29. We're almost there. All right, which of the following reactions will be fastest? So we can see that the nucleophile Br is the same for all of them. All right, so really what we're looking at is comparing leaving groups. Okay, what we're doing is comparing leaving groups. Okay, and so here the best leaving group is very electronegative and large, big. All right. Is hydrogen a good leaving group? Nope. All right. C, is a carbon electronegative? No. All right. So we're comparing OH and this, what we call a tosylate. Tosylate group. All right. And that's commonly shorthanded as OTS or OTOS. All right. I can tell you now, again, I had a bunch of ranking questions, not ranking questions, but I had some of these pulled up in my prior video on SN1, SN2. I'm telling you now, if you see an otosylate group as a leaving group, you can't really beat that. All right. That's one of the best leaving groups that we have here in organic chemistry that you're going to see. All right. That will win. Okay. And in that video, I do touch on why. But if you're comparing your OH versus an otosylate group, you're going to have that be the better leaving group. And so if that's more likely to leave, then the quicker a carbocation is formed, which leads to a faster reaction. Okay. So this is talking about the transition state. Okay. Excuse me. Right, so I'm going to do a little bit of drawing board. I mean, not on board, on screen. All right, so first and foremost, we need to ensure that we're even dealing with bromoethane. All right, so bromoethane, remember, is CH2, CH3. already draw this as bond line. All right. B and D aren't even bromoethane. If you look here, Br is bonded to one carbon, and that's a methyl. Where is the other methyl? Or where is the other carbon group? It's not there. All right, so this is not even bromoethane. All right, so don't get tricked by that. All right, and if you were to draw the Lewis structure out for cyanide, what you're going to get is this. Okay. All right. And this is the difference between A and C. All right. This leaving group is going to leave, giving you a partial positive on that carbon, in which there's going to be a bond made between not the nitrogen, but the carbon, giving us the answer A. All right. C has that cyanide backwards. C is implying that the nitrogen is what's acting as the nucleophile, and that's not necessarily the case. Okay. Right. So this is a great question. It's asking what's the curved arrow mechanism for the intramolecular reaction? Right. Is there a D? No. Okay. So I'm going to draw this on the board. Again, I think I even did this question on the prior video. Right. So what happens here generally is that your leaving group's got to leave for there to be a carbocation that gets made. All right. Again, I like to draw things out to make things explicit. Left, leaving your carbocation. All right. So that carbocation is going to come in and make a bond with that carbon, creating a ring. Okay. And then that's going to be positively charged. All right. That's not beneficial though. All right. We would love that nitrogen to not have the excess hydrogens and be neutral, which is where our NaOH, our base, comes in. All right. So that Na dissolves away. And now we're dealing with a nucleophile or a base also in this case. That OH would love to become water. How can it do that? It's going to take an OH. Where's it going to get that OH? From the extras on the nitrogen, giving you answer is going to be C. Okay. Again, I think I do in fact go over that in the other video. Again, towards the very end is when I touch on intramolecular reactions. Hopefully that makes a little bit of sense, and hopefully that provides a good example. So last question. All right. So we need to determine, is this a SN1 or an SN2 reaction that occurs? All right. This is again something that I emphasized in the previous video. All right. To determine if something is a SN1 reaction or SN1 or SN2, we need to look at the substrate first. And if necessary, the nucleophile. All right. is so between these two, the BR is going to be our leaving group. All right. And that leaving group, is it primary, secondary, or tertiary? It's going to be secondary. Okay, so tertiary is going to be SN1, primary is going to be SN2. All right, now we need to look at the strength of the nucleophile. All right, we're in this gray area. Now we need to look at the nucleophile. All right, this is in fact, polar aprotic. Polar aprotic. All right, so like dissolves like polar. All right, this K, or pardon me, scribble that out. K is going to dissolve away, leaving you with that iron. Okay, so this is considered strong. All right, so a negatively charged nucleophile generally is going to be considered strong. Something that's neutral, it's going to be weak. Okay, strong is going to give you an SN2 reaction. Weak is going to give you this. Okay, so based off of what we know so far, we know that B is not going to be an answer choice because BR was our leaving group, not the other. And same with C, BR was the leaving group. All right. Now we're looking at A and D, and the only difference between the two is the stereochemistry. Okay. Remember, SN2 not keeps. Let me undo that. It flips the stereochemistry. Okay. Our BR was wedged. So after an SN2 reaction occurs, it's going to end up being dashed with our nucleophile. So what's our answer? D. Okay. D. So that is an overall kind of a practice exam for a organic chemistry test that touches on nomenclature, Newmans, SN1, SN2. All right, so hopefully this does give a good overview or provide some more practice problems and problem solving for those problems. All right, again, I told you I wasn't going to go too much into theory, in which hopefully I did not, because that's not what my goal is for this video. My goal for this video is to walk through problem solving for a practice test in Marco 1. All right, so hopefully this is a good video that you can like or provides some level of insight into questions that you may or may not see and how they were solved. All right. So again, if there are any corrections that need to be made, definitely don't hesitate. Again, I'm more so a physiologist than I am an organic chemist. So I can make mistakes. If you catch one, definitely don't hesitate to message or comment. Okay. Have a good one and best of luck on your exam.